Picture this. You toss a ball into the air. You expect it to slow down, pull back by gravity, make a nice little arc, and fall back to Earth. It's a basic law of nature, right? It governs everything from an apple falling from a tree to our planet's orbit around the sun. Now, imagine you throw that same ball, but instead of slowing down, it just leaves. It rockets away from you, faster and faster, accelerating into the sky with a force you can't see and can't explain. That's exactly what our universe is doing. For decades, we thought the expansion of the cosmos, the great rush from the Big Bang, was slowing down. We were sure of it. Gravity, the architect of galaxies, should be putting the brakes on everything. But we were wrong. Something mysterious and invisible, a force that makes up more than two-thirds of everything, is pushing the universe apart. This isn't science fiction. This is the biggest unsolved mystery in all of cosmology. Scientists call it dark energy, and it makes up about 68% of our universe. We can't see it, we can't touch it, and we can't measure directly. We only know it's there because we see what it's doing, making the entire cosmos accelerate away from itself. Figuring this out isn't just for academic brownie points. It could reveal the ultimate fate of reality itself. Are we headed for a cold, empty future? Or will the universe be torn apart, atom by atom, by this relentless power? This is the story of that mystery. There is something very strange happening to our universe. Think of it as a cosmic crime scene on the grandest scale imaginable. The victim? Our understanding of physics. The evidence? A universe that's running away from itself. And the prime suspect is an invisible force that, by all accounts, shouldn't even exist. To understand just how deep this mystery goes, we need to rewind the clock, back to a time when we thought the universe was a much simpler place. For most of the 20th century, the story of the universe seemed pretty settled. Back in the 1920s, astronomers like Edwin Hubble made a mind-blowing discovery. He saw that distant galaxies weren't just sitting there. They were all moving away from us. And the farther away a galaxy was, the faster it was speeding away. This was the signature of an expanding universe, the echo of the Big Bang. This discovery changed everything. The universe wasn't a static stage. It was dynamic, evolving, and had a history. A history governed by the most powerful force we knew, gravity. As described first by Isaac Newton and later, with stunning elegance, by Albert Einstein's theory of general relativity, gravity is the master conductor of the cosmos. It pulls matter together, builds stars, sculpts galaxies, and keeps planets in their orbits that Etzo, when cosmologists pondered the ultimate fate of this expanding universe. They saw two main possibilities, both dictated by gravity. Scenario 1. The universe has enough stuff in it for gravity to eventually win the tug-of-war. The expansion would slow, stop, and then reverse. Everything would rush back together in a final, fiery big crunch, a mirror image of the Big Bang. Scenario 2. There isn't quite enough matter for gravity to stop the expansion. In this case, the expansion would slow down forever but never quite stop. Think of a car running out of gas, but coasting on a perfectly flat road. It keeps moving just slower and slower. For decades, the big debate was which one is it? The answer depended on how much stuff was in the universe. The game was to count it all up and see which way the scales would tip. Nobody, and I mean nobody, predicted a third option. Nobody expected the expansion to be speeding up. That would be like that coasting car suddenly slamming on the accelerator with no driver and no engine. It was unthinkable. Then came 1998, the year everything changed. Two separate teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, set out to settle the debate for good. Their plan was brilliant. Use a special kind of exploding star, a type Ia supernova, as a standard candle. A standard candle is an object whose true brightness is known. If you see a candle in a dark field, you don't know if it's a bright candle far away or a dim one up close. But if you know all candles of that type have the exact same brightness, you can calculate its distance just by seeing how dim it looks. Type Ia supernovae are these perfect candles. They happen when a dead star called a white dwarf sucks matter off a companion star. When it hits a very specific mass, it goes boom in a spectacular, and more importantly, predictably bright. Explosion.by finding these supernovae in distant galaxies, the teams could measure two things: how far away the galaxies were from the supernova's dimness, and how fast they were moving from the redshift of their light. By comparing these two numbers, they could map out the history of cosmic expansion. They could finally see if it was slowing down as the data rolled in. Both teams felt a growing sense of disbelief. The results were impossible. The most distant supernovae were dimmer than they should have been. This meant they were farther away than any model predicted. The only way to explain it was that the expansion of the universe hadn't been slowing down. In fact, for the last several billion years, it's been accelerating. The discovery was so world-shattering that the team spent months trying to find a mistake in their data. But the conclusion held firm. Perlmutter, Schmidt, and Reese will win the Nobel Prize in Physics in 2011 for finding that some unknown energy was overwhelming gravity on a cosmic scale, pushing the very fabric of space-time apart. Astrophysicist Michael Turner gave this mysterious force a name: dark energy. The investigation had begun. So, what is this stuff that's bossing around the entire cosmos? The honest answer? We have no idea. Dark energy is just a name we've given to the thing causing the acceleration. It's a placeholder for our own ignorance. But while we don't know what it is, we're starting to get a picture of what it's like, and it's deeply weird. First, dark energy is in charge. When you add up all the stuff we can actually see, stars, planets, gas, you name it, it amounts to less than 5% of the universe. Another 27% is a different mystery called dark matter. The rest of it, a whopping 68%, is dark energy. This means the universe we know is just a foam on top of a deep, dark, and totally unknown ocean. Second, the dark in dark energy is a bit misleading. It isn't dark like the color black. It's dark as in completely invisible. It doesn't interact with light at all. It doesn't emit it, absorb it, or reflect it. You can't point a telescope at it. We only know it exists because of its gravitational effect, specifically its repulsive anti-gravity effect. It's like trying to understand the wind just by watching the leaves dance. You see the effect, not the cause. Third, dark energy seems to be everywhere. Unlike normal matter and dark matter, which clump together to form galaxies, dark energy is spread smoothly throughout space. It seems to be a fundamental property of space itself. It's the energy of the vacuum, the energy of pure emptiness. This is a wild concept. It means if you took a box and sucked out every particle, every photon, every last bit of everything until you had a perfect vacuum, that box would still contain energy. And this vacuum energy has a bizarre property. Negative pressure in our world, pressure pushes out. But the negative pressure of dark energy pulls, creating a cosmic repulsion that stretches space-time. And here's the feedback loop. Dark energy makes space expand, which creates more space, which in turn contains more dark energy, which makes space expand even faster. And it's really important not to confuse dark energy with its equally mysterious cousin, dark matter. They may share a name, but they're thought to be total opposites. Dark matter is a universe's scaffolding. It's a type of matter that doesn't interact with light, but it does have gravity. It clumps together and holds galaxies together. So, dark matter pulls things together. Dark energy pushes everything apart. Dark matter is gravity's buddy. Dark energy is its cosmic arch-nemesis. This invisible, all-powerful entity is our prime suspect. But naming it is one thing. Figuring out what it actually is has become the single greatest challenge in modern physics. Our first suspect is a ghost, an idea from the mind of Albert Einstein himself, which he later called his biggest blunder. The idea is known as the cosmological constant. Back in 1917, Einstein applied his brand new theory of general relativity to the entire universe. At the time, everyone thought the universe was static. It had always been here, pretty much as it is now. But Einstein's own equations told him that couldn't be right. The gravity of all the matter in the universe should cause it to collapse in on itself. A static universe was unstable, like a pencil balanced on its tip. This really bothered Einstein. It went against everything he and other scientists believed. So, he did what any genius physicist would do. He fudged the math. He added a new term to his equations, a factor he called the cosmological constant, represented by the Greek letter lambda, lambda. This lambda represented a hypothetical energy built into the fabric of space itself, an energy that would create a tiny repulsive force, a kind of anti-gravity. He carefully tuned its value to perfectly balance gravity, giving him the static, stable universe he wanted. But then in 1929, Edwin Hubble discovered the universe was, in fact, expanding. The problem Einstein tried to fix didn't exist. His fudge factor wasn't needed. The story goes that Einstein later told a friend that inventing the cosmological constant was the biggest blunder of his life. He dropped the idea, and for 60 years, most physicists just assumed lambda was zero, but you can't keep a good idea down. When the 1998 results came in showing an accelerating universe, cosmologists scrambled for an answer, and there it was. Einstein's old, discarded idea of built-in repulsive force was exactly what they needed. The blunder was resurrected as a leading explanation for dark energy that I end this model. Dark energy is the energy of the vacuum. It's constant, it's everywhere, and its negative pressure is what's driving the accelerated expansion. It's the simplest explanation that fits what we see. The standard model of cosmology is even called the lambda CDM model, lambda for dark energy, CDM for cold dark matter. But this elegant solution has its own horrifying problem. A problem so huge it's been called the worst theoretical prediction in the history of physics. According to our other pillar of modern physics, quantum field theory, the vacuum shouldn't just be calm. It should be a roiling sea of virtual particles flashing in and out of existence. When physicists try to calculate the energy of this quantum froth, they get a number that is outrageously, comically huge. It's a 1 followed by 120 zeros larger than the value of dark energy we actually observe. This is a catastrophe. It's like your theory predicts a table should be taller than the known universe. It tells us that while the cosmological constant might be the right kind of idea, our fundamental understanding of it is disastrously wrong. We're missing something huge that connects our theory of the very big, relativity, with our theory of the very small, quantum mechanics. So, is dark energy Einstein's ghost? It's our lead suspect for sure. But that glaring 120 zeros problem makes a lot of scientists think the real culprit is something stranger. If Einstein's constant is our steady, predictable suspect, our next suspect is a shapeshifter whose behavior changes over time. This idea is called dynamic dark energy, and its most popular version is a theory known as quintessence. The name comes from the ancient Greeks, who imagined a fifth element that made up the heavens. In cosmology, quintessence is a hypothetical energy field that fills the universe, like a magnetic field. But unlike the cosmological constant, the energy of the quintessence field can change and evolve. Think about it. In the early universe, this field might have been weak, letting gravity build the first stars and galaxies. Then, as the universe expanded and matter spread out, the quintessence field could have woken up, its repulsive force growing stronger over time until it started driving the acceleration we see today. This is an attractive idea for a couple of reasons. First, it could help with that worst prediction ever problem. If the energy isn't a fixed number but an evolving field, maybe it's just a coincidence that it has a low value it has today. Second, it might solve another cosmic puzzle, the coincidence problem. Why do we happen to live in the one era where the density of dark energy and the density of matter are roughly the same? Matter thins out as the universe expands, but a cosmological constant doesn't. That we're alive right at the moment they're in the same ballpark seems awfully coincidental. Some quintessence models get around this by suggesting the dark energy density tracked the matter density for most of cosmic history, only recently pulling away. Most excitingly, a dynamic dark energy might explain some weird little hints that are showing up in our latest data. Big projects like the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI, have suggested the universe's expansion might not be perfectly consistent with a constant lambda. The hints are still fuzzy, not yet statistically significant, but they open the door to the possibility that we're seeing the first signs of dark energy's true, dynamic nature. But quintessence has a darker, scarier sibling. If this energy field can change, what if it can increase over time? This leads to a terrifying possibility called phantom energy. If quintessence is a gentle, evolving force, phantom energy is a runaway train. its density would increase as the universe expands, creating a super acceleration. The repulsive force would grow exponentially, becoming infinitely strong in a finite amount of time. This isn't just a math exercise. If we live in a universe dominated by phantom energy, our fate isn't a quiet fade to black. It's a violent, spectacular end known as the Big Rip. The shifting phantom of quintessence is a compelling suspect, but its more menacing form points to a destiny for our universe that is almost too awful to imagine. The identity of dark energy isn't just a cosmic mystery. It determines the fate of everything. The future of reality itself depends on what this force turns out to be. We used to think it was either a big crunch collapse or a big freeze, endless coasting. Dark energy changed the default ending, but as one of our more exotic suspects, the story could get a lot more dramatic. Let's run through three main scenarios. If dark energy is just Einstein's constant, steady and unchanging, then our universe is in for a long, slow, and lonely end. The accelerated expansion goes on forever. Galaxies that aren't already tied to us by gravity will be pushed away faster and faster. Over billions of years, those distant galaxies will cross a cosmic horizon and vanish from our view. Their light will be so stretched by expanding space that it will never reach us. The night sky will get darker. Eventually, anyone looking out from the Milky Way will see only our own local group of galaxies in an endless, empty void. Fast forward trillions of years. The stars will all burn out, leaving behind a graveyard of black holes, neutron stars, and cold white dwarfs. Even these will eventually decay or get swallowed by black holes. And over unimaginable spans of time, the supermassive black holes themselves will evaporate through Hawking radiation. The final state is a heat death or big freeze, a cold, dark, empty cosmos where everything is spread so thin that nothing can ever happen again. A universe that's run out of road. It's a peaceful, if pretty depressing, ending. But what if dark energy isn't constant? What if that quintessence field starts to fade? Some recent hints from the DESI survey suggest dark energy might be weakening. If that's true, the acceleration could slow, stop, and even reverse. In this scenario, dark energy's repulsive force would fade away, and gravity would take over again. The expansion would halt, and the great contraction would begin. The big crunch. Galaxies would stop running away and start rushing toward each other. The universe would get hotter and denser. Galaxies would collide and merge. Stars would be ripped apart. The temperature would soar until atoms themselves were torn to pieces. In the final moments, everything, matter, energy, space, and time, would collapse back into singularity, just like the one that started the Big Bang. Some theories even suggest this could trigger a big bounce, creating a new universe in an endless cycle. This idea, once dismissed, is now back on the table. This is the most terrifying fate. The one we get of phantom energy is real. If dark energy's density grows as space expands, the repulsive force gets stronger without limit. This ends in the complete annihilation of everything. This is the Big Rip. The timeline is chillingly specific. About 60 million years before the end, the phantom force will be strong enough to tear apart galaxy clusters. The Milky Way will be flung away from its cosmic neighbors. With 3 months to go, the phantom force would shred the Milky Way itself. About 30 minutes before the end, our solar system would be unbound. Earth would be ripped away from the SUN in the final seconds. The Earth itself will be torn apart. Then the atoms, with a fraction of a second to go, even the strong nuclear force would fail, and atomic nuclei would be ripped to shreds. The end comes when the expansion rate becomes infinite. Every particle is isolated from every other. The fabric of space-time itself is torn apart. It is the most violent and total end imaginable. Our universe's fate, a cold freeze, a fiery crunch, or a violent rip, all comes down to nature of dark energy. The case of the runaway universe is anything but cold. All over the world, scientists are building incredible tools to hunt for clues. The Dark Energy Survey, DES, just finished mapping hundreds of millions of galaxies. The Dark Energy Spectroscopic Instrument, DESI, is now creating the biggest 3D map of the cosmos ever. And up in space, the Euclid telescope is on a mission to map the dark universe with ridiculous precision. These projects use multiple lines of evidence. They look for more of those type Ia supernovae that started it all. They also measure something called baryon acoustic oscillations, BAO, which are basically fossilized sound waves from the early universe that left a faint pattern in how galaxies are distributed. This pattern acts like a giant ruler, letting us measure the expansion history with amazing accuracy. But these new, ultra-precise measurements are starting to show some cracks in our standard story. The biggest one is called the Hubble tension. It's a stubborn disagreement in how fast the universe is expanding right now. When scientists use data from the early universe, like the afterglow of the Big Bang, and use our standard model to predict the current expansion rate, they get one number, about 67 kilometers per second per MPC. But when they measure the rate directly using nearby stars and supernovae, they get a consistently higher number, around 73 kilometers per second per MPC. For years, everyone hoped it was just a measurement error. But the more precise the measurements get, the more the tension sticks around, leading some to call it a crisis in cosmology. This tension could be a huge clue. It might be telling us our standard model is wrong. Maybe dark energy isn't a constant. Maybe our theory of gravity is incomplete. Or, as some recent studies suggest, maybe we just live in a big cosmic bubble that's less dense than average, which would make the local expansion seem faster. This is where science gets really exciting. The hints from projects like DESI and Euclid suggest dark energy might not be constant. We are gathering clues at an unbelievable rate. The next decade promises to be a golden age for cosmology. We might finally get enough evidence to unmask the culprit and solve the universe's greatest mystery. We start with a fact that turns common sense on its head. Our universe is expanding faster and faster, pushed apart by an invisible energy that makes up 68% of everything we've looked at the suspects. Is it Einstein's ghost, the cosmological constant, a simple and steady force? It's a leading theory, but it comes with that little problem of being wrong by 120 orders of magnitude. Or is it a dynamic, evolving field like quintessence, whose true nature we're just starting to glimpse? That path could solve some nagging puzzles, but opens up wild new possibilities, from a cosmic rebirth in a big crunch to total annihilation in a big rip. Or maybe the answer is something we haven't even dreamed of yet. The case remains wide open. Dark energy is one of the most profound and humbling mysteries in science. It's a constant reminder that for all we know, we are just scratching the surface. The universe we see, all the stars and light, is just a tiny fraction of what's really out there. We're surrounded and governed by forces we don't understand, but the investigation is moving forward. We are living in a remarkable time, on the verge of discoveries that could rewrite the story of our cosmos. The ultimate fate of our universe is written in the nature of this dark energy. And while we may still be in the dark for now, the quest to finally turn on the lights is one of the greatest adventures we've ever been on. What do you think dark energy is? A constant force, an evolving phantom, or something else entirely? Let us know your favorite theory in the comments. If you enjoyed this trip to the edge of what we know, hit that like button and subscribe for more adventures into the frontiers of science. And please share this with anyone else who loves to wonder about the big questions. For those who want to learn more, we put some links in the description. Thanks for joining us.